Hello everyone, my name is Kilari Bharachandra. I am from Chemical Engineering Department VNIT Nagpur. In this video, I am going to present and explain about Universal Testing Machine. So before going deep down into the topic, I would like to explain how I came across this analytical equipment and what is the significance of this equipment. So I used to wonder what are the materials that are used in the automobile industry or the metals used in the aerospace industry, or what are the even if you consider the glass which is used in the mobile phones are given. And like you consider in the mobile phones they were given a specific the specific weight or specific force that it can withstand. So even if you consider in a tempered glass, so all of these materials we consider like metals, non-metals or composites glass, they go under a testing, and they were given ISO certificates, like you can see ISO 9000 certificate and everything. So how these certificates, and I mean the ISO stands for International Standardization uh, Organization. So this standardization, as we may consider how this standardization is given. So in this way I came across this analytical equipment called Universal Testing Machine. So the universal part, you might wonder what why this universal part is there in this testing machine. uh, because universal testing machine almost uh, gives the all I mean it can perform many standard tensile and compression tests on materials, components and structures. So it can perform bend tests, it can perform what you can say standard tensile stress, tensile tests and compression tests and many more. So let's go into the topic. And before going into the topic, I would like to explain what are the things I'm going to cover in this video. So in this video I'm going to cover about the schematic representation of the universal testing machine, and how UTMs, I mean universal testing machines, are classified, the working principle of the universal testing machine, and the types of tests that can be conducted using the universal testing machine, and how the results we can I mean how the results we can analyze, and how the results are calculated in the universal testing machine softwares, and what is the raw data that can be produced in the universal testing machine, and what is the process data that is produced in the universal testing machine. So the final report output studies are also being discussed in this video, and finally the applications, the advantages and limitations of this analytical equipment is discussed in the next parts. So coming to the schematic representation, so as you can see there are 7 parts. I mean you can majorly say there are 7 parts in this analytical equipment. So this is the upper crosshead, and this is the movable crosshead. So by moving the movable crosshead you can place your specimen here. See, this is the space for tensile specimen. So if you are going to conduct a tensile test, then you are going to place your metal, composite or non-metal, whatever it is, in here. So if you are going to I mean consider you are going to compress, I mean you are going for a compressive test, you are going to see what is the compressive strength of a concrete, let us consider. So you are going to place it here. So for tensile specimen here, and for compressive specimen here. And this is the table where we can place the compressive specimen. And next we have a table here where we can place it. So and this is this is the I mean this is the part that will separate the universal testing machines. I mean we'll classify in the next part, I mean in the coming parts. And this is the load indicator, and this is a speed control. So what are the components of a universal testing machine? As we can see, load frame. It is a rigid structure that houses the moving and stationary components. And we can see here, this is the load frame, and it comprises of the stationary parts and the movable part. And crosshead, a movable beam that applies force to the sample. And this is the crosshead that applies force in the compressive or tensile tests, and grips or fixtures. It holds the sample securely during testing. The types depend on the tests. These are the grips that hold the sample in the tests we are going to perform in the universal testing machine. And load cell, it measures the applied force with high precision. And extensometer is an optional component, as you can say. It measures the deformation or strain in the sample. And we are going to discuss the what is the elongation and deformation and everything in the upcoming part. So next, the control panel. It manages the test parameters and records the data. And this is the one I'm going to talk about, the drive system. It powers the crosshead movement, either hydraulic or electromechanical. So this is the drive system I'm going to talk about now. The drive system, it says that it powers the crosshead movement, either hydraulic or electromechanical. So it here we comes. Okay, so before going to it, these are the roles and what are the data produced by each of the component. As you can see, grips or fixtures, crosshead, load cell, extensometer, and these are the roles of these components, and these are the data that is produced by these components. And yeah, so coming to the classification part, I'm going to majorly discuss in brief about electromechanical UTMs and hydraulic UTMs. So in electromechanical UTMs, the mechanism is simple. It operates using an electric motor coupled with a screw drive mechanism to move the crosshead, and the speed is controlled electronically, so it offers high precision. So the advantages are suitable for low to medium load testing and high accuracy and control over load application. So this is where the drive system is being the electromechanical is being differentiated with hydraulic. And the applications are tensile compression and bending tests for smaller specimens like plastics, rubbers, and thin metals are being conducted in these electromechanical UTMs. Whereas if we come to hydraulic UTMs, the mechanism is slightly different. It uses hydraulic oil pressure to drive the crosshead and apply force. And this is the crosshead I'm talking about. It uses the hydraulic oil pressure it to drive the crosshead and apply the force. It is capable of handling very high loads up to several thousand kilonewtons. So generally, hydraulic UTMs are being used for high loads, like we can say high density metals or anything. So the advantages, coming to the advantages, it is ideal for testing high strength materials such as steel and concrete, and it has a robust design for heavy duty applications. So the applications are structural testing, large scale tensile and compressive tests, and testing of heavy duty materials. So this is the classification. I have discussed only electromechanical and hydraulic UTMs, and this is the general classification. As if you consider, it is based on static and dynamic and micro UTMs, high temperature UTMs, and environmental UTMs. And this is the operating mechanism in each of the UTMs, and these are very user specific. If you consider, let's just say, uh, dynamic or fatigue, it has an operating mechanism of with cycle load. And every UTM here has a different purpose, but mostly hydraulic is used because of the metals, and it has a high, what we can say, it can handle very high loads up to several thousand kilonewtons. So this is the load capacity, and these are the primary applications, as you can see. So how do we prepare the sample? The sample preparation can vary based on the purpose of testing, and in general cases the samples are cut in a dumbbell shape. The shoulders of the test specimen are kept broad as compared to the testing area. So coming to the working principle, I'm going to discuss about the hydraulic UTM in deep. And this is the definition of the hydraulic UTM. The high pressure oil pump supplies oil to the working cylinder, and through the movement of the piston, the platen and the upper beam, the upper jaw set, are pushed upward to perform the tensile or compression tests of the sample. So this is the this is the specimen, space for tension test and space for compression, bend or shear or fixture test, as I have discussed, and this is the load cell, and this is the oil cylinder I'm talking about. So the working principle is very simple here. It works on the principle of elongation and deformation. These machines usually use a hydraulic cylinder to create the force. The applied force is determined by system pressure, which can be accurately measured. The tensile test, as I have discussed, is carried here, whereas the compressive test is carried here. The adjustment of test space is achieved by the drive mechanism, elevating motors, sprocket, chain, etc., and driving the double screw to rotate synchronously to raise and lower the moving beam. And we will discuss what are the types of tests that can be conducted in universal testing machines. The first test I'm going to discuss is tensile test. So in the tensile test, uh, we have to uh, we have to open the holding grips and place our specimen in here, and we have to close the grips. So so clamp a single piece of the specimen on each of its ends and pull it apart until it breaks. This measures how strong it is, the tensile strength, how stretchy it is, the elongation, and how stiff it is, the tensile modulus. So this is the stationary base and this moving crosshead I have explained here. Yeah, and this is the moving crosshead, and it will move up, and what until it breaks, the moving crosshead will move and it will record in the UTM software. And these are the tensile specimens that are used. Not going to discuss about it, it's for reference. So the second one being compression test, the exact opposite of tensile test. This is where you compress an object between level plates until a certain load or distance has been reached or the product breaks. The typical measurements are the maximum force sustained before breakage, or load at displacement, or displacement at load. And this is how the compression test is being conducted. And coming to peel test, so we can also perform a peel test in universal testing machine. This is but as we have discussed tensile test and compressive test, this is very similar to tensile test. However, instead of pulling apart a single piece, you pull apart two materials that have been bonded together. In this test, you clamp, one holds one material and the other clamp holds the other material. Then you pull apart for a few inches. The force is measured up to 1000 times per second during the test, and the average of all the force readings are reported as the average peel force. And bending test. Uh, uh, Contrast to the peel test, this is a compression test where you support a length of material by spanning it across two supports on each end. Nothing is supporting the middle portion underneath of it. Then you press down from above directly in the middle of span of material until the supported material breaks or reaches a specific distance. So the test measures how strong the material in flexural strength, and how stiff it is. So as you can see here, it is a U-tube like structure, but we can use a 2-point structure. Like you can hold you can hold like a point here and a point here, so that a 2-point structure can be tested. Or otherwise, instead of 2-point, you can also put a sharp point here instead of U-tube like structure. So this is the graph we this is the graph we see in the software of the UTM in a computer. And we can see this, the load is being given in the y-axis, and travel, the length, is being given in the x-axis. So what are the applications of this output? So we will discuss applications in the end, but what is the applications regarding this graph? It gives material development. It helps in selecting suitable selecting materials with suitable properties. It helps in quality control. It ensures materials meet performance criteria. It also helps in design validation, simulating real world loading conditions. It also helps in failure analysis, as I have discussed before, in identifying causes of material failure. So, graphical output. In universal testing machine, as we have seen that load versus travel is being given as an output graph. So what can we conclude from this graph? So in the x-axis, after processing, we can also obtain a stress strain curve in which the x-axis contains strain. It is denoted by epsilon, and in y-axis we have stress, which is denoted by sigma. The key points, as we have studied in even in the 12th, uh, the Young's modulus, Hooke's law, and proportional limit, elastic region, yield point, plastic region, ultimate tensile strength, fracture point, and these are the points that can be given in the graphical output of this graph. So load displacement graph. So what we have, I mean, this is the raw data we have obtained. This is the load displacement graph I am talking about. So in the x-axis we have seen that delta L, in y-axis we have force. It uses it reflects raw UTM output, useful for interpreting machine specific behavior. Yeah, this is the raw data how I'm talking about, and the duration also it is recorded in the UTM. So the derived data, how the data is being derived. So I will discuss very simple basics thoroughly. We know the stress is equal to force per unit area, force that applied per unit area, and A refers to the cross sectional area of the specimen, and units are pascals or megapascals. And coming to strain, it is the change in length per the original gauge length of the specimen, and it is a dimensionless as expressed as a percentage. And we have Young's modulus E. uh, E refers to stress by strain. It is calculated in the linear elastic region of the stress strain curve. I will discuss the linear elastic region in the coming next slide. So let's just understand what is ultimate tensile strength. And maximum, it is the maximum stress the material can withstand before necking or failure. So generally the ultimate tensile strength is the maximum strength the material can withstand, whereas the yield strength is something, I mean, I'll show the graph. Yeah, so this is the point D. This is the ultimate tensile strength. So let's just say we have a chair, and the chair material is something of a fiber and plastic mixture, or something called or something of a fiber. So this is the ultimate tensile strength refers to the most, I mean, the maximum stress that material can withstand before necking or failure. So how it differentiates with the yield strength? It is a stress at which material begins to perform plastically. So this is the yield point. I'm referring to yield strength. uh, After this, the material, so before that we will understand what is this proportional limit, and why this is x and y axis is coming to be linear, and stress and strain. So until proportional limit, the material the material obeys Hooke's law, and until that point the material is fine. I mean, even after the until this particular force, if you stop the testing, then the material deforms to its original shape. And after this elastic limit, what it happens is, if you cross this particular point, the material will not deform to its original shape, and it will deform. That's what I'm saying in this yield strength. And this is what I'm saying, stress at which the material begins to deform plastically. So this is the plastic region I'm talking, and this is the Hooke's law, and this is the fracture or breaking point at which the material will break. And yeah, so this is a typical curve of a typical curve of a metal or any plastic material. So sometimes the curve tends to come like this. So you can see here uh, the graph is linear up to certain point, but instead of proportional elastic limit and yield point, there is nothing specified here. So we don't know what is the yield point here. So for materials without a clear yield point, we cannot know where the material will not deform plastically. So for this we have 0.2% offset method, which identifies the yield strength by finding the stress corresponding to a permanent strain of 0.2%. So this is how we calculate yield strength using the 0.2% offset method. So we plot the stress strain curve at first and use the data from the tensile test from a UTM and plot the stress y-axis and strain x-axis. So after that we have to determine the elastic region. So what is the elastic region here? It when it obeys the Hooke's law, as you can see here. Here we have a linear line, y is equal to x line. Here up to this point we came across that it obeys Hooke's law. So similarly here too, as you can see up to here, maybe we can say it obeys Hooke's law. So after this we have to we have to identify the linear region of the curve where Hooke's law is applies. Sigma is equal to E into epsilon. And after that we have to draw the offset line. So what is the offset line here? We have to take 0.2% offset and draw a line parallel to this linear line. And after that, at 0.2%, as I'm saying, draw a line parallel to the linear portion. The slope of this line is equal to the modulus of elasticity. Then we have to use this equation of a straight line. Sigma is equal to E into epsilon minus 0.002. So after that we have to locate the intersection point and extend the offset line until it intersects with the stress strain curve. The stress value at its intersection is the yield strength of the material. So in this way we calculate the yield strength using the offset method if the material doesn't have a yield point. And yeah, that's it. And we have studied about graphical output until now, and the final report output. And this is the report output I am talking about. And we get raw data, force displacement data during the test, and process data, stress strain curve, which are being processed in the UTM software, which also gives the mechanical properties such as sigma y, UTS, E, elongation, etc. And the visual representations are being shown for the graph. These data is being shown in a visual representation. And compliance comparison with standards. We get International Organization for Standardization and ATSM, which stands for American Society for Testing and Materials, and we get these comparisons too in the modern softwares. So what are the applications of a universal testing machine? So applications are very simple here. We are able to perform the tests of the materials, compression, tensile, bending, and everything, and even peeling also. And here that's what I'm mentioning, material property testing. And by this we can quality control and assurance also being is a major application, as you can see in automotive industries, aerospace industries, constructions, textiles, everywhere. Even in the textiles, as you can see, measuring tensile and tear strength of fabrics. So it is important that important to note that what are the lightweight materials like titanium and carbon fiber composites in the aerospace industry. And even in the construction fields, the testing of concrete, steel, and wood for structural integrity. So failure analysis is also being done during this, and fatigue is also being calculated. I won't divert the topic to material science, so I'm just limiting here. And even in the product development too, we can perform this. We have these applications. And this is the summary of the applications I'm talking. These are the sectors and these are the purposes and these are the examples you can refer it to. So the advantages the advantages are being it assesses the strength of materials, and UTM offers enhanced control and stability during a materials testing process. It also helps ensure accuracy and repeatability. The range of tests is so wide that it allows for testing a wide range of materials under different conditions, different speeds, loading rates, forces. Actually, we we can vary these speeds and forces, everything, and UTM need relatively little maintenance and are easy to fix in the event of a breakdown. So they have a little maintenance cost and they have very less chances of failure. So coming to limitations, majorly it is the major limitation is being the very difficult to customize. The very little customization is there in the universal testing machine, and it produce initial system that is more expensive to build and maintain, and it require training of maintenance staff, and that is a minor limitation, and it is maybe difficult to use with the existing system. And these are the references I have used for this topic and presentation, and thank you.